isotope analysis just changed the very timeline of how Earth was born in the very early days of the solar system. Baby Earth took a much shorter time to form than we previously thought. According to a new analysis of the iron isotopes found in meteorites, most of Earth took just 5 million years to come together, several times shorter than current models suggest. This revision is a significant contribution to our current understanding of planetary formation, suggesting that the mechanisms may be more varied than we think, even between planets of the same type, located in the same neighborhood, rocky planets, such as Mars and Earth. You see, we're not really 100% sure about how planets form. Astronomers have a pretty good general idea, but the finer details, well, they're rather hard to observe in action. The broad strokes of planetary formation process are bound up in stellar formation itself. Stars form when a clump in a cloud of dust and gas collapses in on itself under its own gravity, and starts spinning. This causes the surrounding dust and gas to start swirling around it, like water swirling around a drain. As it swirls, all that material forms a flat disk, feeding into the growing star. But not all the disk will get slurped up. What remains is called the protoplanetary disk, and it goes on to form the planets. That's why all the solar system planets are roughly aligned on a flat plane around the sun. When it comes to planetary formation, it's thought that tiny bits of dust and rock in the disk will start to electrostatically cling together. Then, as they grow in size, so too does their gravitational strength. They start to attract other clumps, through chance interactions and collisions, gaining in size until they're a whole dang planet. For Earth, this process was thought to have taken tens of millions of years. But the iron isotopes in Earth's mantle, according to scientists from the University of Copenhagen in Denmark, suggest otherwise. In its composition, Earth appears to be unlike other solar system bodies. Earth, the Moon, Mars, meteorites, all contain naturally occurring isotopes of iron, such as Fe56 and the light Fe54. But the Moon, Mars and most meteorites all have similar abundances, while Earth has significantly less Fe54. The only other rock that has a similar composition to Earth's is a rare type of meteorite called chondrites. The interesting thing about these meteorites is that they have a similar composition to the solar system as a whole. Imagine if you were to get all the ingredients for a bolognese. Mix them all together in one big pot, that's the protoplanetary disk, and later the solar system. But if you scattered your ingredients into a bunch of smaller pots, with different proportions of each ingredient, now you have the individual planets and asteroids. What makes chondrites special is that in this analogy, they are like teeny tiny pots containing the initial proportions of ingredients for a full bolognese. So, having one of these space rocks on hand is like having a microcosm of the dust that swirled around in the protoplanetary disk at the dawn of the solar system, 4.6 billion years ago. According to current planetary formation models, if things just smooshed together, the iron abundances in Earth's mantle would be representative of a mix of all different kinds of meteorites, with higher abundances of Fe54. The fact that our planet's composition is only comparable to CI dust suggests a different formation model. Instead of rocks banging together, the researchers believe that Earth's iron core formed early through a rain of cosmic dust, a faster process than the accretion of larger rocks. During this time, the iron core formed, slurping up the early iron. Then, as the solar system cooled, after its first few 100,000 years, CI dust from farther out was able to migrate inwards, to where Earth was forming. It sprinkled all over Earth, basically overwriting whatever iron was in the mantle. Because the protoplanetary disk, and the large abundances of CI dust in it that could have rained down on Earth, only lasted about 5 million years, Earth must have accreted within this time frame, the researchers conclude. This added CI dust overprinted the iron composition in the Earth mantle, which is only possible if most of the previous iron was already removed into the core, explained planetary geologist Martin Schiller of the University of Copenhagen. That is why the core formation must have happened early. If this cosmic dust accretion model is how Earth formed, this research also means that other planets elsewhere in the universe could have formed this way. This not only broadens our understanding of planetary formation, but it could have implications for our understanding of life within the universe. It could be that this kind of planetary formation is a prerequisite for the conditions conducive to life. Now we know that planet formation happens everywhere, that we have generic mechanisms that work and make planetary systems. When we understand these mechanisms in our own solar system, we might make similar inferences about other planetary systems in the galaxy, including at which point and how often water is accreted, said cosmologist Martin Bizarro of the University of Copenhagen. If the theory of early planetary accretion really is correct, water is likely just a byproduct of the formation of a planet like Earth, making the ingredients of life, as we know it, more likely to be found elsewhere in the universe. Please save the trees and nature. Please subscribe my channel. Thank you.